Hello, my name is Eric Grigori, and in this video we're going to cover robot localization using particle filters. So I wrote all the code used in this video, and all that code is available up on GitHub. I only ask that you follow the license described in the header of the files. This is the robot that the software was designed for and that it will eventually be tested on. Right now I've only tested the algorithm in the simulator that we'll talk about in a minute. The robot, if you look on top, that blue circular object on top, that's a 360-degree single plane Lidar. It's that data that we're going to use to localize the robot. In addition to the Lidar data, there's also a magnetometer. So the robot sends the Lidar data and the magnetometer data to the particle tracker. And the particle tracker uses that data to localize the robot on a map. Currently, the software I'm going to show you right now is all running in a simulation. I also wrote the simulator. The simulator uses OpenCV graphics because I know OpenCV graphics, and simulates a robot and in order to test the particle filter. The code is written in such a way that the particle filter is driven by the data from the robot. So later on it'll be easy to receive the data from the robot and input it into the particle filter. And that'll be the next step. So the simulator has three parts. The first part is the arena. The second part is the blue dot, which is actually the simulated robot. And then the next part is actually the visualization of the particle filter. The simulated robot, the blue dot, sends simulated LiDAR data to the particle filter. On the right, you see what simulated LiDAR data looks like. Basically, the way to do the simulation is we scan around where the robot's location, the simulated robot's location, and we send out a, quote, ping until we come across a white area. The white area are the boundaries. The black area is the open area. So we go around, we scan, we send out these pings, we measure the distance to the white area, to the boundaries, and then we create a single, a one-dimensional list. This is written in Python, so it's a one-dimensional list. This one-dimensional list now represents a 360-degree spin of the LiDAR. The software is written in such that the LiDAR zero location, the zero location in that list, is always the front of the robot. So that's what that arrow shows going around the robot. So the net result, if you plot the data, is you get a nice visualization of what's around the robot in a single plane. The only data the particle filter has to work with is the LiDAR data from the robot and the magnetometer data from the robot. So the particle filter knows, it has a picture of what's around the robot, in a single plane, and it knows which direction the robot's pointing in, but it has no idea, initially at least, where the robot is in the room. So you can see here the blue dot being the robot and the green dot being a particle. What the particle filter is working with is what's on the right-hand side here, which is LiDAR profile data. So from here, it's obvious if you look at the graph that the robot and the LiDAR are surrounded by different surroundings. Okay, what their LiDAR data is seeing. Remember, this is all simulated. What their LiDAR data is seeing is different. And the hypothesis is that if the LiDAR data is different, the robot's in a different location. So this is an example of where the LiDAR data looks very similar, but in fact the robot is in a different position than the particle. Remember, in this case, you have each hypothesis of the robot's position is represented by a single particle. So in this case, we're just for demo purposes, we're running a single particle. So the particle has the particle filter has a hypothesis that the robot is located where that green dot is at, and that hypothesis is based on the fact that the LiDAR data actually looks close. But as you can see, the particle filter is completely wrong, and that is where the algorithm, having the right algorithm comes to determine the actual location. And we'll see how this progresses as we go forward. In a non-temporal environment or a static situation, you really can't use the particle filter to tell where the robot's at. There may be some tricks to doing it. It may be possible, but it's a lot more difficult. If you add a temporal component and you say, okay, what I'm going to do is I'm going to take a look, I'm going to compare my LiDAR data. What I'm going to do is I'm going to drop a whole bunch of particles. I'm going to look at all their LiDAR data, and I'm going to find the ones that match the robot as closely as possible. Then the robot's going to move, and I'm going to move my particles the same way as the robot. So the particle filter actually has a model of the robot. So when the robot's going to transmit back, actually in addition to the LiDAR and compass data, it's going to transmit back approximately how much it moved. So the robot might move a foot and then stop and then take LiDAR data, take compass data, and send it back. That temporal component now is what the actual particle filter algorithm uses to try to determine the exact location of the robot. When we first start the particle filter, it has no idea where the robot's at. So what happens is the particle filter waits to get data from the robot. So it's just sitting there waiting. The robot then sends the LiDAR data and its magnetometer data. The particle filter will then create a number of hypotheses. So each dot here is a hypothesis. It's the particle filter thinks the robot might be here. And they're color-coded based on how confident the filter is that the robot's at that location. Now this is based strictly on the LiDAR data. So what it's doing is it's correlating the LiDAR data for a filter, for the particle. It's correlating that data with the LiDAR data from the robot. And based on that correlation, we generate a weight. How similar are the two signals? The more similar, the green dots represent the particles that have a more closely relationship. In other words, the LiDAR data, the shape of the LiDAR data most closely matches the shape of the LiDAR data for the robot. So the green particles are high confidence. The red and the yellow particles are low confidence. As you can see, the particle filter at this stage has absolutely no idea where the robot's at. Actually, I say absolutely, but it thinks it may be where the green particles are at, but it's not sure. And you can see that by the confidence values. By moving the robot only a single step, so what happens here is the robot now, after sending its data to the particle filter, it moves. So let's just say it moves one foot in a direction. It then stops, sends its LiDAR data and its magnetometer data to the particle filter. After only that single movement, you can see that all the hypotheses, all the red and yellow hypotheses have gone away. Not yellow, but all the red. And now the particle filter has a much better idea of where the robot is at. And again, the actual location of the robot is never sent to the particle filter. This is strictly based on LiDAR data and magnetometer data. Oh, and distance data. The robot also sends how far it moved. So just based on that data, the particle filter's already got a pretty good idea of where the robot's at. A much better idea than it had initially. After just a few more steps, the particle filter is locked in. It knows almost exactly where the robot is at. Now, just because it's locked in doesn't mean it can't lose lock. And because remember, the robot moves a foot in a direction. It sends that data to the particle filter. The particle filter has a robot model in it. So it doesn't know exactly the motion of the robot. It just knows that the robot moved a foot in a general direction. It has a model that it uses to calculate the next position of the particles. That model is not precise. It's not accurate. In fact, we actually intentionally add a little noise to it. So the net result is that the particle filter can actually lose track of the robot. So the reason that noise is actually good in this situation is because it's actually possible for the particle tracker to lock on to the wrong position. So it's very possible, and you'll see that in the video later on, where the particle filter thinks another group of particles is the robot, and it's completely wrong. So you don't want it to get into a situation where it locks in and it basically gives up trying to find the robot. So by introducing a little bit of noise, it guarantees that if the particle filter is wrong, after a couple of steps, it'll try again to try to find the robot. In this case, you can see that that noise has resulted in the particles scattering a little bit, but it still has a really good idea where that robot's located at. As discussed, the algorithm is actually quite simple, and I really like particle filters for tracking purposes because they're so organic. So basically, if you think of each filter as an independent entity, if you think of each particle as an independent entity, that particle thinks it knows where the robot's at. And then all by itself, that particle moves, sort of by itself. It gets the same data. It gets the distance data and the Lidar data from the robot. But because the way the noise works, it has its own little personality. And it's actually the combination of multiple particles and the averaging of multiple particles that you get the actual final result of the robot. Now, it's important, though, that particles that sort of go rogue, particles that are really way off, those have to be cleaned up. They have to be removed. And so that's a big part of the algorithm is how do you determine what particles to remove? How do you determine what particles to group around that have the highest probability of being the robot? And this discusses that. You can look at it in the code. It's actually quite simple. It's not all that complicated. But you can look at it in the code. It's about a half a page. The whole algorithm is about a half a page of code. So this is the code, and as you can see, it's quite simple. I had to cut out some things to get it to fit on one slide, but this is basically the algorithm that decides what particles stay and what particles go. So here you can just see a video of the particle filter actually in action. And something you'll note is it stops trying to track when you're going over the dark regions, the all black regions, because without any data from the LiDAR sensor, which is what those regions indicate, there's really nothing to track. So the red dots, those regions, the small red dots, those regions indicate valid data from the LiDAR sensor. In other words, the robot is close enough to a wall to actually get something out of the LiDAR sensor. But you can imagine a particle filter is not going to work at a robot in the middle of a desert because there's nothing bouncing off the LiDAR sensor. There's nothing to work with. So and that's another good point. A robot walking down the middle of a wide hallway that doesn't have any, in this next video, I've added some code to help visualize what the particle filter is, quote unquote, thinking. So there's a big purple circle. The size of that circle is the confidence that the particle filter has about the robot's location. And in theory, the particle filter is going to try to circle the robot. So here you can see that the particle filter has a very low confidence. It has really no idea where the robot's at because the circle is so big. And in fact, the robot is in a completely opposite place. So it's completely wrong here. This is an example of where the particle filter is actually tracking something that's not the robot. And it's why we have to add some noise and clean up particles. So in this video, you'll actually see the particle filter prediction. So here, particle filter has no idea where the robot's at. The robot's in the lower right corner. The circle's huge. Particle filter thinks the robot's, now it's getting, okay. Again, the particle filter has no idea where it's at. It's going to go ahead and reset. So here, the particle filter, it got completely lost. It's going to say, okay, I'm going to reset. So now it still thinks the robot's at the top there, and it really doesn't have any idea where the robot, and then now it's locked in. And if you look really closely, you can see that. See, now it's lost lock again. You can see so now it's got a good idea, and as the circle gets smaller, now it has now it's very confident. There's also a confidence number next to the W average up there is a confidence number. 1.0 is absolute sure. But you can see that the particle filter is pretty confident that it knows where the robot's at. And L, the numbers next to the L, are the filter's prediction of where the robot's at. And R is the actual position of the robot. So I learned about particle filters from Dr. Thrun's AI for Robotics course at Georgia Tech's OMSCS program. You can take his AI for Robotics course on Udacity. I highly recommend it. It's a fascinating course.